Ladies and gentlemen, my name is Rafael Piskigarski. I'm here to present you the work titled Failure History Analysis in Traction Systems using Multidimensional Scaling and Neural Networks. The main topics are objectives, introduction, methodology, data acquisition, multidimensional scaling, neural networks, results, and conclusions. The objectives of this work are develop a study of traction-related failures of an electric drivetrain with direct current traction motors, collecting information in the existing database and proposing actions that assist in the resolution and reduction of traction system failures. Using these presets, statistical modeling on the raw data, focusing on DC traction motor failures, including corrective and preventive maintenance information, analyzing the influence of multiple factors, and using multidimensional scaling in neural networks to investigate these failures data. This work was developed inside a metropolitan transport company in Porto Alegre, in the south of Brazil. A fleet of trains composed of 25 trains of 4 cars of Japanese manufacture with traction by 8 direct current motors, operating for approximately 35 years. Fault identification of any nature is done manually by the pilot. The train does not have an event register with much relevant information for traction failures. These failures are mostly high level, which means the train must finish its journey and return to maintenance area. The methodology for this presentation work follows the order of chronology, information, and focus. First step was acquire the data from failures from 2008 until 2018 for traction failures. Review intervention requests, order of service, and checklists manually and digitally. The second step was transform subjective data into quantitative data, creating a master table and dividing equipment that has suffered some interference in systems. The next steps used multidimensional scaling method and neural network methods in this table to find some relations. It was made some alterations of this master table during this analysis and was included information about preventive maintenance, creating new tables. As said before, the data acquisition was made manually and digitally in a software used internally to follow the opening and the closure of the failure. The first master table created had 545 fails opened, with 893 descriptions of repair that was transformed to 197 types of repair. Information in this table includes the date, the fail level, the gear point, the stretch or section in the railway, the speed, the motors affected, and the repair details, like the substitution of the motor, the collector was blown, or changed some protection items. These 197 reduced repair information was divided in 12 systems for this work. Traction system subdivided in traction motor pieces, actions on motor, traction control, extra fast circuit breakers, overcurrent relay, and protective elements. High voltage system subdivided in pantograph, line switches, and switch keys. The other 3 are not essential electrical equipment. They are the operation system, errors or duplications, and the pneumatic system. These are some graphical results found with multidimensional scaling. For each variable, in this case the proposed system, was used 2 or 3 dimensions to correlate a dimension to a system. As we can see, the variable st.1 traction motor, and for another traction systems, there are points that go beyond the division. For the protective elements st.5, quadrant divisions did not provide information. The S-stress variable increased by increasing the dimension, despite the figure become more clear. We could expect otherwise, and for this reason, we started to use the neural networks. The first software package for neural network was IBM SPSS. It was created 8 scenarios selecting motor positions, gear points, the proposed subsistence, or the stretches. The factors was the other columns in the master table. The output analysis was the confusion matrices. Another analysis was made with the same software, but with a modification in the subsystem for traction motor. The division was based on one type only for items replaced and the other type for only actions in motor. It was created other 7 scenarios to analyze only these subsystems. They will be shown in the results for neural networks. The output was the same as before, the confusion matrices. Another package of neural networks programs used in this work was the machine learning of MATLAB. It was created 36 scenarios and the output was the confusion matrix, the scatter plot, the ROC curve, and the parallel lines. Some peculiarities of this environment are the focus on motor, the 2 scenarios for the dependent variable fail code and the other for the motor subsistence, was added information about preventive maintenance and created 3 new master tables called flashover. Some variables columns required to change and others left blank. Now talking about the results from the neural networks analysis, the skating sensation and the anti-skating system. It has an increased accuracy in positions 1 and 3 of motor cars. The model SP1 counts the data with skating and anti-skating the tests. The model SP2 does not. The stretches as a dependent variable had very low accuracy. That's because we only consider failures and not normal operation. The accuracy of gear point 2 is greater than the gear point 3. It has a transition from one point to another that is necessary to investigate better. It contradicts the statistical information of the motors that have a high failure rate at point 3 than at point 2. We can see in the table above the influence and correlation of the subsistence. It can be used also as an order for fault repair. In the model SP5 has only the subsystem as a dependent variable, but the others are not included as factors. Model SP6 has all the subsystems included as factors. Overcurrent relay, switch key, master control, and pneumatic subsystems, when they have faults, they are inside their own system. The system that suffers the most interference from others is the traction control. In the table below, the subsystem ST.16 has the influence of internal motor elements, because Model E had only subsystem with correlate variables of ST.1. The subsystem ST.A4 has the influence of external elements, because Model B does not have a related subsystem ST.A. Another result from this work is the use of only one code for traction failures, definition by analyzing the confusion matrix. With data not filled, it has a lot of NaN values. It has influence in the analysis. Systems and subsystem divisions demonstrate the value of proposed tables for the use of neural networks. The flashover table number 8 including the maintenance revisions for trains and dividing it in systems becomes an interesting practice for future investigations. The ensemble bagged trees is the best PCA method verified in this study. With a quantitative analysis, if we want to generate a scatter plot for a specific variable, another method may be more accurate. The action of blowing motor has a low accuracy rate for the system. We need 2 other parameters. But the data indicate that it does not have this activity when skating sensation is present. It needs to monitor this skate sensation, make a frequent cleaning, and or changing the motor filter method. About the subsystem ST16, the complete motor. The skating sensation has the standard deviation above the others, as do high voltage systems, due to the low variation of values. This is also seen in ST.84. About the speed, a fault identification in a model at speeds below 70 km per hour has a better occurrence percentage than at speeds above 70 km per hour. It may be because of transition of gear points. Conclusions about this work. It presents a new methodology for testing and modeling failures that affect and degrade the operation of electric multiple unit trains, adding these issues to the phase of specification of maintenance requirements. It results in detailing of documents represented by tables and specific methods for the modeling and specification of non-function requirements. It is satisfactory and innovative in the use of neural networks within the railway area. Thanks all for your attention.